Okay, chapter 7. Oh, any problems that you run across in the interim that we need to take care of? I think what we'll do today is, since we don't have a lab, I'll have time to finish the entire, get that out of the way. I'll have time to finish the entire chapter today. And then on Thursday, we can spend Thursday looking at the lab. All right. So let me get all my equipment together here. Chapter 7. We're going to be discussing what makes up an atom, how the atom is structured, how it's built from the ground up, from the subatomic particles up, and then what effect that has on periodicity. And that directs your attention to the periodic table. The periodic table is structured a certain way. And once you learn how it's structured, you can use it to build atoms. So we'll get there eventually. So where does the information come from that how do we know about the structure of atoms? It's exclusive, well, almost exclusively. There are other avenues, but most of what we know, and historically, information about the atom has come through light. Different colors of light tell us different things about the atom. We just had to learn how to interpret them. We know that we can get different colors from fireworks by putting different elements in the burst charge. And some colors are easy to get, and some of them are more difficult to get. So why do we get, these are questions that we want to answer. Why do we get these different colors? When I was working for the USDA and had various pieces of equipment available to me, one of those was called an atomic absorption spectrophotometer. Basically what it was an acetylene flame. And you aspirate your sample through the flame, and then you shine a beam of light through it. And the elements are dissociated and separated. They're individual elements in the flame. And then you shine the light through them, and wavelengths of light would be absorbed by the elements as it passes through. And you read it on the other side, and you see which ones are absorbed. And the decrease in the intensity of the light indicates an increase in concentration of the element. So we use that to calibrate the instrument and determine concentration of elements in our samples. Well, the other nice thing about it was, when you aspirate your sample, depending on what's in it, it can give you some really nice colors. And some of these examples, typically used for flame tests, which is a qualitative approach to identifying elements. That's sometimes successful and sometimes not. But I would aspirate, we'd have usually high school groups come through the lab, and I would usually fire that thing up and ooh and ah with different colors blowing through the flames. And I think my favorite was hot pink, strontium. Strontium. Oh, well, potassium, yeah, that gives kind of like a, let's see, here it is. There, yeah, potassium. Actually, strontium is a pinker color than potassium.
Hot pink.
Hot pink. Yeah, it's very bright. So kids like that one. But for understanding what color, the relationship of colors to the elements happen to be, we need to be a little more quantitative about it. What makes a color in quantitative form, and that's what we're getting at next. In addition to that, the color of the flame will be different if the flame could be different than the same element in solution. So you have some difference in chemical associations in the solution than you do in the flame. In the flame, what you're doing is you're completely divorcing the element from any of the other components of the carrier. And so you actually see the individual atoms of the element emitting light. In a solution, you may see a different color because more often than not, the element hydrates. It's associated with water, and that association with water changes how it absorbs light. So it may be one color in the flame and a different color in a solution. So what we want to do is also determine why some of these colors are common to different elements. Yellow seems to be extremely common in flame tests. So that's why it's difficult to use flame tests to distinguish one element from another, because they're so similar, and the eye has a certain sensitivity to different colors, and the lines are blurred. So we need instrumentation that can parse out those differences. The ones that appear the same color may not be exactly the same. So when we look at these different associations of the elements, we find that they're perfect examples in nature of the influence of the form of the element and the color associated with it. If you slice open an artery before the blood has too much time in the air, it will be bright red because the artery is taking oxygenated blood to the body. So that bright red is an association of iron in the hemoglobin molecule. It actually has 4 proteins around it. And it associates with oxygen, 1 or 2, I can't remember how many. But that association with oxygen changes the color, and it's a bright red. But if you slice a vein open, it's going to come out kind of a purplish color because it's no longer carrying the oxygen with it. So we have these various complications that make interpreting colors, or what the instruments tell us the colors are, it's difficult to interpret them unless you have a guide sheet or a game plan. And that's also where we're headed. When I was working on my master's, we were trying to figure out a way to, this is in Louisiana. There was a growing industry of processed crawfish. So they would boil the crawfish, they would break the tails off, pull the meat out, package it, freeze it, send it all over the world. Well, there's a lot of waste because the tail meat in the crawfish is only about 15% of the mass. So you got a lot of waste. So that was part of my task as a master's student, trying to figure out what to do with this waste. One thing we noticed was that the shells of boiled crawfish is bright red. So we looked at possibly using that in certain animal feeds. Farm-raised salmon very often has dull meat, right? Versus wild-caught salmon will be bright red because in their food chain, they pick up these compounds here, these carotenoid compounds. They're called that because they're related to carotene, right? Vitamin E. And they deposit them in their flesh. So we say, okay, well, maybe we can recover some of these carotenoids from the crawfish waste and use those incorporated into diets for salmon or other animals that need the color. But why is it red, right? Some of these, let's see, I'm going to try to use this pointer since it won't be recorded up there. Some of these are close to red, right? But you'll notice that there's no sodium in this molecule. So they're red here, they're red there, red hemoglobin. They might be the same color, but they're the same color for different reasons, right? The reason that this molecule, astaxanthin, is red is because it has these double bonds in here. Double, single, double, single, double, single. Those are, and the words just flew out of my head. They're conjugated. They're conjugated double bonds. And the more of those you have strung together, the redder you get. You go from the blue end down to the red end of your spectrum. So, let's see. The answer to this is addressed in a discussion of electromagnetic radiation, which is light. Now, we call it electromagnetic radiation because light has both an electrical component and a magnetic component. And they're typically described as occurring right angles to one another. So the magnetic displacement in the light beam will be this way, and the electrical will be this way. Okay, so we need to know something about light. All right, so we characterize light, and historically speaking, light was first characterized as a wave. And in many respects, it is a wave. But we're gonna throw a wrench in the gears in a few more slides. But in order to describe a wave, we have typically waves are represented as sine curves. If you remember, if you got it in math, I don't know if you did in math class, this is noticed as a sine wave. And this would be displacement, and this would be time. So over time, you get an amplitude change. Okay, so the wavelength, and these waves are moving. Right? So the wavelength would be the distance between two crests. Right? That would be a wavelength, and we give it the small letter lambda from Greek. That's the wavelength. And of course, the SI unit for length is a meter. Right? So the wavelength would typically be designated as meters. And we're going to modify that later, but for now, that's good. You can also characterize this wave in terms of frequency. And whereas here we measure the length between crests, in frequency, we say a fixed point, say right there, and we watch it. And we count how many waves pass that point in 1 second. So since the wave is not a unit of measure, how fast it occurs, say waves per second, then the actual unit of measure is reciprocal seconds. Okay, how many waves per second? And we also give that another, a unit of measure that honors one of the pioneers in electromagnetic radiation. His name is Hertz. So we use Hertz as for frequency, but frequency means reciprocal seconds. And then we have the speed of the wave. How fast does the wave, does this crest go from here to there, right? So many meters per second. So I hope you can see that the wavelength divided by the frequency, and the frequency is given the symbol, the letter nu, which is a Greek letter. Looks like a V, but it's pronounced nu. So the speed of the wave, the velocity, is equal to the wavelength divided by the times, excuse me. Times, because this is meters and this is reciprocal seconds, so that's meters per second. There you go. There it is. Now this is true for any wave. Waves on the surface of a lake, sound waves, the speed is equal to the wavelength times the velocity. But for our purposes, we're talking about light. So light gets a special speed. It's a little c, right? Speed of light. And this is, we typically describe it as speed of light in a vacuum. In speed of light in air is a little bit slower, but not much. And then it also changes depending on what material it's passing through, which means if the speed of light changes depending on the medium, that means light is actually interacting with the matter that's in the medium. It has to in order to make that change. Okay, so that's our fundamental equation. Speed of light equals its wavelength times the frequency. And we typically, in a vacuum, the speed of light is 2.9979 times 10 to the 8th meters per second. That means, since this is a constant, if we know one of these, we can calculate the other one. Okay. Let's see. That's just a representation of different wavelengths producing different frequencies. So if the wavelength gets bigger, let's see, if the wavelength gets bigger, say from here to here, then the frequency has to get smaller. Okay, they're inversely related. It's like, I probably mentioned it before, but if you have a constant equal to a product, then that's an inverse relationship. It's like Boyle's law. We haven't got there yet, have we? We've done Boyle's law. Okay, good. So that's pressure times volume equals a constant. That's an inverse relationship. This is an inverse relationship. Okay, so the electromagnetic spectrum, as far as we can tell, covers a very wide range, and most of it we can't see. The rods and the cones and the retinas of our eyes are only sensitive to a very narrow band of wavelengths. We can go from, let's see, we can go from very short wavelengths, gamma radiation, all the way up through X-rays, ultraviolet, and into the visible range, right? And then we can go even longer wavelengths into infrared, microwaves, radio waves, and that has subdivisions also. We're gonna describe the amount of energy that's carried in a wave in a few minutes, but as a qualitative description, the shorter the wavelength, the higher the energy. And of course, the shorter the wavelength, the higher the frequency. So high frequency means high energy, low frequency means lower energy. And if we look at the visible range blown up here, we see that it is very narrow. In fact, 10 to the minus 7th meters, it's all of the wavelengths are contained within that size of a measurement. Between 4 and 7 times 10 to the minus 7th meters is the full extent of visible wavelengths, right? And everybody learned the colors of the rainbow in grade school, right? Boys, you did. The one I never could figure out was indigo. Violet was pretty easy to find. Blue is even. Where's indigo? I guess they needed something to fill in that space. It's right in here somewhere, I guess. Okay, and there's another unit of measure that you will typically see. It's called the nanometer. It's wavelength. So 1 nanometer is equal to 10 to the minus 9th meters. Okay, that's what nano means. Nano means 10 to the minus 9. So in terms of nanometers, well, let's just take 4 times 10 to the minus 7. Right, this is meters. we want to convert that to nanometers. Right, so we want nanometers on the top and want meters on the bottom. So for every 1 meter, they're 10 to the minus ninth. Excuse me, let's do it this way. 1 nanometer is 10 to the minus ninth meters. There we go, that's better. Okay, so meters cancel, and 10 to the minus ninth now in the denominator, come in the numerator, it becomes plus, right? 10 to the ninth. So that's 100 times, isn't it? 4 times 100, minus 7 and plus 9. So that means 400 nanometers is the blue end of the spectrum, right before you get to ultraviolet. And then, of course, 700 is at the other end. So the visible range is between 400 and 700 nanometers. All right. So, in keeping with the concept that energy cannot be created or destroyed, like conservation of energy in the universe, then any type of energy that you put into that pickle has got to go somewhere. Right? So we got high voltage into that pickle, and it probably stinks, right, as it heats up. You're volatilizing compounds, and you're also cooking the pickle. But notice that some of that energy turns into light. So if you account for all the forms of energy, the energy going in by those electrodes, and then you say, all right, where does it go? Well, it goes into heat, it goes into chemical breakdown, chemical changes, and some of it turns into light. All of those together is equal to how much energy went in. But some of that energy is light. And for the longest time, the only type of lighting that we had was Edison's lighting. It was incandescent light bulbs. All he did was he drove an electric current through a filament in a bulb that was, I think they tried evacuation, but found that wasn't practical. So they filled it with an inert gas. So there wouldn't be any degradation of the filament due to any reactions when it heated up. You heat that filament up and it emits light.
Will it explode?
That pickle?
Yeah.
Possibly, but I don't think so because we've punctured it and given a place for gases to escape. Now, if you stick it in a microwave, yeah, it probably would explode because its skin would be intact.
Sweet, so God.
You gonna try it out?
Yeah.
Okay, put it inside a container or something so that when it explodes, it won't mess up your microwave. Okay, so energy can be converted in various forms, and we can use the wavelength or the color of light to determine how much energy is being emitted by that light. That's where we're headed next, with a little history. Okay, so this guy, James Clerk Maxwell, was a brilliant mathematician. And he came up with the first set of usable formulas to address the nature of electromagnetic radiation. And at that time, he and everyone else around him, because of the success of his equations, believed that light was only a wave. That's it. That was the end of the story. Light was always a wave. Okay, we're not going to get into his equations in detail because they're really complicated. The equations are still valid today. When light can be treated as a wave, under certain circumstances, that theory falls apart. And we're going to talk about that too. So at the beginning of the 20th century, 1900 in that range, most scientists believed that we know it all. From now on, it's just a refinement of details. Were they in for a big surprise? So we get work from Max Planck, who was a physicist and a pretty good mathematician of his own. He was studying a phenomenon called black body radiation. That just means that if you have a chunk of something, matter, and it was non-reactive, in other words, it would not produce light on its own by some chemical reaction, so to speak, or nuclear reaction for that matter. But it was just a black body. It was like a chunk of charcoal. Then if you heat it up and get it hot enough, it'll start to glow. And the hotter you get it, the shorter the wavelength. It would go from red, kind of a red glow, and then it'd go through the yellow, and it'd go, as you get it hotter and hotter and hotter, it become more toward the blue range. In fact, we use that correlation now to determine the temperature of stars. You see some stars, you've heard of red giants, they have a cooler surface, and they have blue dwarfs. They're really hot. And then there's our sun, which is kind of in the middle. It's more like a yellow. But that black body radiation concept was found to be valid and correlated with temperature. What he discovered was that energy can be gained or lost, but only in whole number multiples. And the energy that's gained or lost is equal to, this energy is equal to the frequency of the light times a constant that he developed. So it's called Planck's constant. And what we're saying is that energy is equal to frequency. And this is our fudge factor to make the units match up. Okay, so that was the first step. And that the energy of the light, the energy contained in that light beam at a given frequency is proportional to the frequency, and it occurs in what they called packets or quanta. So energy is quantized in its transfer. Now, that was the first indication that light was not just a wave. It could also be considered as a particle. It could be considered as having mass. Okay, there's more to come. This was Planck's equation, but sometimes we don't have the frequency, but we have the wavelength of light instead of the frequency. So all we have to do is use this other relationship, right? Like that, solve it for frequency would be C over lambda, and substitute that in here. And now we have an equation that we can use if we know the wavelength instead. It's either that or do two calculations. So either one of those works. And there's Planck's constant. It's not a number that I expect you to memorize. It'll be in the useful information. Okay. Oh, you got a movie. Let me see. Oops. Do I have to start it? I may have to start it myself.
Everybody knows Albert Einstein for his theory of relativity and the Nobel Prize he won for it. He also... What? I didn't win the Nobel Prize for relativity. I won it for explaining the photoelectric effect. Right, of course, sorry. Einstein won the Nobel Prize for his work on the photoelectric effect, which helped settle the age-old debate of what light is made of. So, what is it? Okay, let's rewind a little. Newton had thought light was made of particles, and his rival Hooke had thought it was a wave. Technology advanced enough, some experiments proved Hooke was right. That proof, and Maxwell's equations describing light's behavior as a wave, made the debate die down, until the photoelectric effect was discovered. When light hits a cable next to another cable, electrons jump from one to the other. It was thought it happened because waves of light made atoms vibrate until they ejected an electron. But when it was measured carefully, a big contradiction was found. It only happened for light of some wavelengths. For others, no electrons jumped at all. Einstein was bewildered. The photoelectric effect should work regardless of the type of light. If light wasn't made of particles, and now it turned out that it couldn't be made of waves, what was it made of? After much reflection, he formulated a new hypothesis combining the two previous ones. What if light were made not of waves or particles, but of both? That is, what if light were made of wave packets? That concept, which we now call photons, allowed Einstein to write out equations that explain the photoelectric effect in 1905. This consolidated the idea that light can sometimes be described as a wave, sometimes as a particle, and sometimes as either. It was a revolutionary view, and it opened the field for quantum physics. Robert A. Millikan, an American experimental physicist, was unconvinced by Einstein's conclusions. So he set out to prove him wrong by carefully measuring the photoelectric effect. However, years later, Millikan ended up proving Einstein right, and they were both awarded the Nobel Prize in Physics.
Okay. So Einstein, and this was while he was a patent clerk in the patent office at Bern, Switzerland. He was so proficient at reviewing patents, he'd get most of his patents done in a few hours in the morning. The rest of the day, he'd sit at his desk and do this kind of stuff, just scribbling on paper and formulas and all that stuff. Anyway, so what does the photoelectric effect have to do with the quantum nature of light? Well, these are the observations. No electrons are emitted by any metal, and this is usually referred to or reference the photoelectric effect in terms of metals, because metals, are more ready to give up electrons in chemical reactions, and nonmetals like to receive electrons. So the photoelectric effect is seen in metals predominantly, and I can't think of a single example where the photoelectric effect, except for one, silicon. Silicon is the base for most of our microelectronics and our photocells. Anyway, if you're looking at a pure metal and light is shining on it and you're measuring the ejection of electrons, you won't see any electrons ejected by that metal except for those that are above a certain frequency. The threshold frequency for that metal is different for every metal. Okay. Then we also observe that below this threshold frequency, no electrons are emitted, no matter how intense the light. So if light were behaving purely as a wave, if you increase the intensity of the light, that should be more energy on the metal, and you should get electrons ejected eventually, but it never happens. It only happens relative to the frequency of the light, the energy. We use Planck's equation. Right? You need a certain amount of energy in this packet, this photon, in order to eject a single electron. Now, that may be one of the points coming up, so I don't want to steal my own thunder. Right, the ejection of electrons by light that exceeds the threshold frequency increases as intensity increases. So once you've got the frequency high enough to eject electrons, you can get more of them if the intensity increases. But you can't get any by just increasing the intensity. Okay, so once you've got this threshold frequency, the threshold frequency, if you increase the frequency beyond the threshold, this is just the bare minimum energy required for the electron to leave the surface. If you increase the frequency further, then that gives you more energy. So the electron acquires enough energy to be ejected, and the rest of the energy goes into the kinetic energy of the electron. And you can measure how fast those electrons are moving, and there are various ways to determine the threshold energy. Okay, so these are the conclusions. Electromagnetic light must arrive at the surface of the metal in discrete packets. It's quantized. These are called photons. Now, don't ask me how they make a photon torpedo. That's science fiction. And each quantum or each photon of light has to possess a minimum amount of energy in order to cause the electron to exit the surface. Now, any photons, remember, we're conserving energy. So any of these photons that reach the surface of the metal, but they don't have enough energy to eject an electron, that energy has to be absorbed somehow. And it's typically absorbed as heat. So you can heat up the metal surface with light without ejecting electrons. Those are called thermal photons. They have less than the required amount of energy, so that energy goes into heat. And here's what I was talking about, kinetic energy. The kinetic energy of the ejected electron increases as the frequency increases beyond the threshold. Intensity then becomes a measure of photon density. In other words, an intensity means that you have more photons per square meter impacting the surface as intensity increases, but you don't increase the energy of the photon unless you change its frequency. Okay. So what does this photoelectric effect tell us about the structure of the atom? Well, first of all, the interaction of light and matter happens at the electron level. So when light encounters an atom, of course, when you look at the structure of an atom, you've got the nucleus and then electrons out here. The first thing that the atom sees, or the first thing the light sees when it approaches, is electrons. So it delivers its energy to the electrons. And if it's high enough, electrons can be ejected from the atom. And in order for the photon of light to eject an electron, it has to be specifically tuned to the amount of energy that's required to move the electron from some level around the atom to a distance of infinity. Once the electron leaves the atom, it has a distance of infinity relative to the nucleus of the atom. There are no in-between levels. We're going to talk about that also. The quantization of energy of light is one of the ways that we get a handle on what's happening inside the atom, movement of electrons around the nucleus of the atom. All right, I've already said that, so I'm not going to go through that again. Well, actually, there is if electrons have kinetic energy, they have to have mass, right? Because this formula means they have a certain velocity, they have to have mass, okay? And in fact, light behaving as a particle also has mass. You've seen the research that's been done with solar sails. You heard of those? You send a satellite up, right? Blast it up into space with a rocket. And then you open this big mylar sail. And the photons coming from the sun are caught by that sail, and it sends your satellite off into space. Now, it's a very low pressure, right? Because photons have low mass, but it's continuous, right? You get that push for weeks and months and years, and eventually you can build up some pretty significant velocities. And it's free.
And you want to have fuel, right?
Huh?
You want to use fuel when you go up there, right?
Right, you wouldn't have to use your own fuel. Yeah. Now, of course, the farther you get from the sun, the lower the pressure, because the inverse square law. But right, until it runs out, it's all free. All you have to do is build it. That's my favorite picture of Einstein. I guess that was at a time when he had already made a name for himself and he could act silly if he wanted to. And I've seen videos of him riding his bicycle, sitting on the handlebars backwards. Okay, so he won his first Nobel Prize for explaining the photoelectric effect. And then very soon after, in fact, most of his work was done early in his career, in his 20s. And he published his special theory of relativity in 1905. Special relativity is it's called special because it's really focused on just what happens when things approach the speed of light. That's all it is. General relativity then gets into a discussion of gravity and space-time. But he was able to prove mathematically that light has mass. Okay. Now, this is not what we normally consider rest mass, like what's my mass? Well, I'm not really sure because I don't think in terms of kilograms. What's kilograms for 200 pounds? Like maybe 80, 85 kilograms, something like that. He's talking about relativistic mass. And when things get moving really fast, closer to the speed of light, their relativistic mass goes through the roof. That's why we generally say that under normal forms of propulsion, we're never going to exceed the speed of light in a spacecraft. Because as you get closer to the speed of light, the mass just goes, and it takes more and more and more energy to get it going. So you got to get around that somehow. And that's where the warp theory comes in. You warp space, then you don't have to deal with the mass. So that's why Star Trek and these other programs have discussions of warp drives, right? They're those big pods on the Enterprise. They're there to warp the space. So it's kind of like surfing a wave, right? You compress the space in front of you and expand the space behind you. Theoretically, it's possible, but it takes a lot of energy. Okay, energy has mass. So this is where he came up with his famous E equals mc squared. So the mass of any object times the speed of light squared is equivalent to its energy. And we've been able to prove that with nuclear reactions. We start off with, say, U-235, and it splits into two atoms. And we can measure the mass of the U-235. We can measure the mass of the products, and there's a difference. The mass of the products have less mass than the original atom after it's before it splits. And we can also measure the energy that comes out of that reaction. And using this equation, we can create a budget, a balance. So if we take the energy back to mass, that mass is accounted for in the energy that's released when that nucleus splits. Okay. Then we come along, see, Einstein was one of those, it's funny, physics is divided into two camps. There are the experimental physicists and the theoretical physicists. Einstein was theoretical. He never walked into a lab in his life, except maybe to visit. But there are experimental physicists that want concrete proof of what these theoretical physicists are proposing. So Arthur Compton was one of them, and in 1922, he confirmed Einstein's equation. Then we come to this dual nature of light. Sometimes it's a wave, sometimes it's particle, and sometimes it's a combination. Right. This photoelectric effect. As long as the photon is traveling through space and it hadn't hit the metal yet, we can consider it a wave. But when it strikes the metal surface, we have to consider it a particle. In other words, it has quantized energy. So in effect, it's both. Everything, light and all mass, anything that has mass, even me, we have wave properties. And they're very long waves. And they're insignificant for practical application. Wave and particle properties only become significant when the particles are really, really small. Right, so both are correct. There was a huge argument going on at the end of the 19th century and the beginning of the 20th century between scientists saying, it's a wave, no, it's a particle, no, it's a wave, it's a particle. There's just back and forth. Scientists love to argue with each other. They finally just had to throw up their hands and say, okay, it's both. So how do we know that light behaves as a wave? Well, there are certain things that light does that can only be explained in terms of waves. One of those is diffraction. Diffraction is it's like, you can explain it like this with a pinhole, and that's a good way to explain it. If we've collimated our light beam so that it's linear, it's coming from a single source, and it strikes this barrier, this pinhole or this slit serves as a source, a new source for a wave. So it tends to radiate out from that source. Okay. You can also do a double slit like this. Okay. So that same light beam can strike this, and now this one produces, right? And this one also produces. And if you think of these lines, these dark lines as crests of the wave, and these as troughs, then wherever the crests meet, you get constructive interference. In other words, the amplitude increases at these points. And where a trough meets a crest, you get destructive interference. And if they're the same wavelength, of course, it just goes flat because you've got the wave going this way in one way, this way the other way, they cancel each other out. Okay. This concept is used in everybody knows prisms, right? You can shine sunlight through a prism and split it into various colors of light. You can do the same thing with what we call a grating. In other words, you can scratch the surface of a glass plate, and if they're very close together, then when you shine light through that glass plate, each one of those scratches, those troughs and scratches, acts as a slit, a source, and then these many sources combine one another. And if you look at it from here over here, you get a grate from blue to red. So that interference allows you to split out the colors just like you would with a prism, only for different reasons. Prism does it one way and gratings do it another way. These can be transmitting gratings or they can be reflective gratings. I used to have an instrument in the lab called an inductively coupled argon plasma spectrometer. And all it did was it took argon gas through a magnetic field, a very strong magnetic field that transferred its energy to the argon and made it very hot, 10,000 degrees or 10,000 K. So we aspirated our samples through there, and then that ripped everything apart, tore all the electrons off, and then we looked at it a little higher as the electrons started to come back. And as they did, they would emit light. That's another topic we'll cover in a second. And we take the light from that beam and shine it through a spectrograph in the instrument. And it would use a version of the grating, only it was a reflective grating. The grating had line ruled on it, and then it had a reflective coating on it. And it did the same thing, only as the light came in, it bounced off that way and split the light beam into various wavelengths. And we could use that to detect qualitatively what elements are in the sample and quantitatively how much there were. So it's a very powerful instrument and very expensive. I think the first one we had there was $250,000. And then when I replaced it, the price had come down. It was only like $140,000. But this is the government, you know, they got money
Yeah, it's not just that.
everywhere. And big companies can afford this. If they need it, then it's well worth the expense. Okay, so this property of diffraction is characteristic only of waves. The other property is refraction. Refraction is like the prism. So when light strikes a prism, say the surface of the prism is like this, and then you have more of it over here, of course. But as the light strikes it, the light slows down inside the material, and it slows down differentially for the wavelengths. Different wavelengths slow differently. So when you get here, then it tends to bend that way. And then the next one comes along and it bends that way. So you get the more the light bends, depending on its wavelength, you can separate the colors. Okay? So that's refraction. As light passes through a substance, it's bent. Difference between refraction and diffraction. Okay. So once we can get the light separated and we can identify its wavelengths, frequencies, which are directly correlated with color, then we can start to say something about the elements that are emitting the light or the elements that are absorbing the light. Right? One of those instruments I used, the first one I described, absorbed light, and the second one emitted light. And they're both characteristic of the same phenomenon. It's the movement of electrons in the atom that determines what those wavelengths are. Okay, and you can, if you're looking at a source like the sun, you're going to get a continuous spectrum, right? All the wavelengths available, and that's typical of black body radiation. It's a continuous source. However, if you have a single element and you excite it and let it emit light, like hydrogen, for instance, then what you get is a line spectrum, in which you get distinct wavelengths here, 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 and here in the visible range. Of course, you can go outside the visible range if you have the instrumentation, but we're only interested in those 4 visible wavelengths. So there's a continuous spectrum. This used to be a little video before, what was it, flash video went the way of the dodo. Now it doesn't work anymore. But it is a good picture of the continuous spectrum. So you have just shine light through a slit to make it linear, and then through a prism, and it'll separate into all the colors of the rainbow.
The discharge tube is filled with hydrogen gas. When a high voltage electrical discharge energizes the gaseous atoms, light is emitted only at specific wavelengths. The emission spectra obtained are called line spectra due to the appearance of bright lines.
Is that it? Okay.
In the hydrogen emission spectrum, there are 4 lines in the visible region. A purple line at a wavelength of 411 nanometers, a dark blue line at a wavelength of 434 nanometers, a green line at a wavelength of 486 nanometers, and an orange-red line at a wavelength of 656 nanometers. Let's look at the electronic transitions responsible for the observed line spectra. When an electron drops from a higher energy orbit to a lower energy orbit, a quantum of energy, a photon, is given off in the form of light. During the electronic transition shown, light is emitted in the visible region of the electromagnetic spectrum. You may click on the buttons to review each of the electronic transitions individually.
So these are energy levels around the atom. We haven't discussed that yet, but we will. Okay, so what do these energy levels mean? Well, first of all, the electron only moves between these individual energy levels. There's nothing in between. If there were in-betweens, then every atom would emit a continuous spectrum because it have infinite number of choices of movement. But these are line spectrums that come from the elements. And that means that the electron only moves between these quantized levels around the atom. Okay, now light is giving us some clues as to how the atom is structured, at least at the electronic level. And that's what I just said. I stole my own thunder again. Right. If the level were not quantized, we'd see white light, just a continuous spectrum. Okay. So, let's see, I'm missing something. Oh, Bohr's model. Okay. Niels Bohr. That was given out pretty soon. Niels Bohr proposed that based upon this difference in energy levels and the line spectra of elements, proposed that for hydrogen, he's starting really simple. Why did he start with hydrogen? Because it's only got one electron. There are no interferences of multiple electrons that would muddy the waters or cloud the understanding. So Niels Bohr said this, he used the planetary model. So the nucleus is like the sun, and then you have these orbits out here for your electrons. Right? And he gave them numbers. This is n equals 1, 2, 3, 4, and they go on up. And these will be referred to as principal quantum numbers. This is the first level of describing the electronic structure of an atom. These are related to the energy of the electron. And notice the closer you are to the nucleus, the lower your energy. And that's based upon the fact that in order to get an electron to go from here to there, you got to add energy to it in order to get it to move up. So the more energy is further away from the nucleus. And if you get enough energy, like our threshold frequency, you can eject that electron out here to a distance of infinity. Okay. All right. So this Bohr model is based upon planetary. And the ground state for the hydrogen atom with its one electron is n equals 1. Now, for other atoms, the ground state is all the electrons are as close as they can possibly get to the nucleus, right? You have electrons here and here and here, and they just fill it up. So the ground state will be whatever the highest electron level is. We'll come back to that later. Notice in this model on the board, excuse me, yeah, the n equals 1 is very close to the nucleus in energy, and then 2 is a big jump in energy. And then as you go higher and higher, the energy levels decrease in their difference between their neighbors. So the jump between, that's why in that video, notice all the jumps were from higher levels down to 2. They never went to 1. If they had gone to 1, they would produce frequencies that were not visible. They would be in the ultraviolet or higher range, more energy. So those 4 wavelengths, and they only show 3 here because n equals 6 is missing. And that jump, that quantized jump, is what is responsible for the different colors, the different frequencies of light. Yeah, what's missing is the forced emission line. So there's another way of looking at Bohr's model. And Bohr's model explained what they knew at the time very, very well. In fact, I'm going to give you an equation here in a minute. Got to mathematically prove it. All right. Let's see. So calculate the energy of an electron for an energy level. That n value enters into an equation. And that equation is here. This was Bohr's equation. And it simply said that the energy is equal to this value, right? Negative 2.178. Notice I don't have it memorized either. Times 10 to the minus 18, that's another fudge factor, joules, times these variables. Okay? So what do those variables mean? Well, Z is the same Z we've always learned. It's the number of protons. It's the atomic number. So for hydrogen, that would be 1. Okay? And N is the energy level, right? 1, 2, 3, 4. So if you multiply this times that figure, you'll get the energy in joules for the electron at that energy level in the hydrogen atom. Now, if it jumps from one to the other, you just need to calculate the energy from the higher level and the energy from the lower level and subtract it. And that'll give you the amount of energy that is either absorbed or emitted for the transfer, depending on whether it's from a higher to lower or lower to a higher. And that energy change can be fit then into Planck's equation. Or you can say that energy, put the energy here, Planck's equation here, you can calculate the frequency of the light. Or you could say, we're more interested in the wavelength usually. So you could solve for wavelength if you know the energy of the transition. So the delta, the change in energy, would be this one minus the other one. And in my way of thinking, the sign is important because it tells you whether the energy is emitted or absorbed. But as far as determining the wavelength of light, regardless of whether it's emitted or absorbed, you only need the difference between the two energies and take the absolute value. And then that can go in here. That's a constant. That's a constant. You can solve for the wavelength. And that will confirm what we've measured. We can measure the wavelength of light at these 4 different emissions from hydrogen and correlate them with these energies. So there's experimental evidence there for that. Okay. Energy is going to be in joules. That's the SI unit of energy, is joules. Energy is 0 relative to the nucleus. Energy is 0 when the electron is at infinity, right? When n equals infinity or the electron is ejected, it's at 0. And it decreases energy as it gets closer to the nucleus. We know that because it emits energy. Okay, let's see. And only 1 electron is present. Now, the interesting thing about this is this equation also works for other elements, but only if they are, how would I say this, hydrogen analogs. So you can put Z in here from a different element. Say like if we go to helium, right? Z would be 2 then. But it's only valid if helium is a +1 charge. We got rid of one of the electrons. Now we only have 1 electron. You can only have 1 electron for this to work. So if we went from, what's lithium's next? Lithium would have to be +2. And beryllium would have to be +3. So that you could, this only works for elements if there's 1 electron left. Okay. That was one of the problems with Bohr's model and this equation, is that it only worked for hydrogen analogs. But it was a beginning. Okay. So this is what you would do for calculating the change in energy for an electron transition. You would have the N would be for the final minus the initial. So in that respect, it's consistent with what we understand delta to be. Delta is always final minus initial. And then once you get that value, and we can simplify the equation. Notice we've factored out this value here and this value here, and we get the Z's over the N squared. That's a little easier to deal with. Let's see. There we go. For hydrogen, of course, that Z will be 1. So for a hydrogen atom, that's the equation. And that should be in useful information. Let me see. Let me be sure it is. I don't want to tell you wrong. Planck's constant. Okay. That equation is not in that form, but we do have the energy equation, the first one I showed you, and then right below it is the delta equation. So you would have to fit the E from each one into that equation. But it doesn't give you that bottom one. All right. So for a hydrogen atom transition from N equals 5 to N equals 2, delta equals 434 nanometers. The change in energy would be this. Okay. Final minus initial of N. So final would be what? 2. Initial would be 5. It's going from 5 to 2. Okay. So if we fill those values in and do the math, the energy should be 4.57 times 10 to the minus 19 joules, which is pretty small, right? But then if we compare that to the calculation using this equation, And notice we had to change the nanometers to meters in order for that equation to work, Planck's equation. We calculate Planck's energy based upon the wavelength at 4.577 times 10 to the minus 19. So they're very close. Okay, so there's the Bohr model. It's a planetary model, assuming that the electrons orbited the nucleus just like planets orbit the sun. But the mathematical descriptors and calculations work. Okay, now we now know that the Bohr model is not correct, but it was a starting point. First of all, it only works for hydrogen. Right? When you start getting 2, 3, 4 more electrons, you get those repulsive forces that change the energy levels. So we need something more sophisticated, a different approach than a nucleus with circular orbits. All right, this is just rehashing those energy transitions. We don't need to spend time on that one. Oh, the longest wavelength will be the shortest jump. That's the point of this slide. So the shortest jump is between 3 and 2. 4 to 2, 5 to 2, 6 to 2, those are bigger jumps. So the longest wavelength will be the lowest frequency and the lowest energy. Okay. All right. So now enters another brilliant mathematician and physicist, Werner Heisenberg. And what we want to take from Heisenberg is what's called his uncertainty principle. So the formula is a product of this, and I'll tell you what that means in just a second, and this. And that has to be greater than or equal to this expression. There's Planck's constant again. Is that pi? Yeah, pi. Okay, what that means is this value, because pi and Planck's constant this is all constant. Right? There are no changes here. The changes are over here. So what he says was, these are inversely related, and these deltas mean that's an uncertainty of position, x being position, or an uncertainty of momentum. And the letter we use for momentum is the Greek rho. Right? So mass times velocity is momentum. Well, if you're talking about a single particle, like an electron or a proton or something like that, then mass is not going to change. So really, you're talking about the difference in velocity and position. So uncertainty of position, since it's an inverse proportion, right? If this goes down, that goes up. So if mass increases or velocity increases, let's say your object is at the same velocity and we're changing mass. Let mass vary. I think it's more instructive that way. If mass increases, then the uncertainty of position goes down. That means for something is my size, there's virtually no uncertainty as to my position. You know where I am, right? There's very little variability there. But if mass gets very, very small, then the uncertainty of position goes way up. So that means for something along the size of an electron or a proton or even an atom, then you may be able to tell how fast it's going, but you'll never know where it is. That seems like an odd paradox there. So that's basically Heisenberg's uncertainty principle. And that was what we were dealing with, because when you got a nucleus with Bohr's model, he's saying that, yeah, I know where these are. They're in that energy level and they're a certain distance from them. And then Heisenberg said, no, they're not. Right. They may be a certain energy, but you don't know that they're there based on this mathematics. So that was another problem with Bohr's model. There are others that contributed. Planck was active in this area. Einstein was active. De Broglie was active. In fact, de Broglie has an equation that will allow me to calculate my wavelength. Schrodinger came along, and he was instrumental in developing the wave functions that would eventually congeal as quantum mechanics. That's the next level of understanding. He had some other things associated with him. I think he was he the one that had the cat in the box experiment? Schrodinger. Yeah, you got this radioactive isotope, and if it decays, it will emit radiation that will kill the cat. But they're both in the box together, and how do you know what's going on in there? You can't see, because when you open the box, you change the conditions. Right. Anyway, Born, Dirac, who's a French guy, and Pauli. Pauli was instrumental too. We're going to see Pauli again when we talk about building atoms. All these people were instrumental in developing quantum mechanics. Okay, we'll come back to quantum mechanics in a minute. But before we do, this wave function, which was produced by Schrodinger's equations, you don't need to know the wave functions, just what this Greek symbol means. If you've ever been on college campuses and you drive down sorority or fraternity row, some of them will have this symbol in their letters. It's the symbol psi, the psi function. The square of the psi function is indicative of the probability of finding an electron in a particular space. So what that means is that quantum mechanics is based on probabilities, right? It's not certainties. It's just probabilities. And you're saying, okay, it's highly probable that a certain electron will be in this sphere around the nucleus. Or we got a different shape, maybe it's highly probable that it'll be in one of these lobes, right? And that'll make more sense in a few minutes. All right. So this wave function that is that has that psi function centrally located indicates probability. So we haven't done electronic structure, have we? No. Okay, so this is not going to mean a lot to you. This 1s is a way of describing an orbital, a location for an electron. Let's let it go at that for now. And this is a probability distribution. So for that particular orbital, as you get closer to the nucleus, the probability of finding it there goes way up. Okay. Another way of looking at it is you're never going to have an electron right on the nucleus, right? So finding it at the nucleus is going to be 0. But at a certain distance from the nucleus, you will have a higher probability of finding it in this region. Let's see. Okay. Yeah, that's an understatement. It's difficult to define precisely the size of an orbital, a probable location of an electron. But as it turns out, The location of electron is not quite as important as its energy. We're more interested in its velocity, its energy, than we are in its location. Probability of finding an electron in a certain location is sufficient. We want accurate determination of its energy. So these electrons, now in quantum mechanics, the electrons, the Schrodinger equations, in order to determine the shape, the probable location, and the energies of electrons, will have 4 numbers that go into that equation. And then it spits out the values that you're looking for. These quantum numbers begin with the principal quantum number, n equals principal quantum number. And this is associated with energy. The energy of the electron is defined by the principal quantum number. Okay, there it is. And these numbers are just like Bohr's numbers. They start at 1 and they go up in whole numbers. So it'll be 1, 2, 3, on. Okay. The next one is the angular momentum quantum number, or L. Angular momentum quantum number. Think of these numbers as nested. In other words, this quantum number can be derived from that one, or if you're at this level, it was derived from that one, or it's derived from that one. And the angular momentum quantum number is associated with the shape of the orbital. And it has numbers based upon these. If this is n, then it starts at 0 and goes up to n minus 1. Okay. So if you're at principal quantum number 3, then you could have a 0, 1, and a 2 within that number. Okay, so it's nested. It's like an expanding tree. The third one is M sub L, which is the magnetic quantum number. Okay, and that is orientation in space. So the probabilities, the locations where you can find these electrons, might be pointing off in that direction, or might be pointing off in this direction. Different directions. And this number is derived from one of these. And it goes from negative L in whole number increments up to 0, up to positive L. So if this one happens to be 2, say we got 3 and we're at 2 for the L, then this one would be -2, -1, 0, +1, +2. So you have 5 possibilities, 5 levels for L equals 2. Okay. Only one more. M sub S. This is the spin quantum number. And this is, let's see what they call it. It's just a spin. You can think of electrons as a top, right? They can spin this way or spin that way. And these numbers are always +1/2 or -1/2. Okay, no matter what you've got coming down to here, say you got a minus L here, I'm saying -2, you're down here. You got a 3, a 2, a -2, and you can have a +1 or a -1/2. Okay, so these four numbers are used to describe the quantum state of an electron. And we've got shorthand that helps us, make this a little easier to write the electron configuration for an atom. And the one that's most used is this one right here, angular momentum. For this one, 0 is called S, 1 is called P, 2 is called D, 3 is called F, and they go higher than that, but that's all we're going to need. In fact, once you get up to F, you're down here. You're about finished with the elements. 118 elements. You can get them all with SPDF. Okay. So if we were to write principal quantum number 2, right? So what could we have for 2? We could have a 0 or a 1. Well, let's say we have a 1. So that would be at n equals 2, and this would be equal to 1. And then we can say how many electrons are there. Right. Well, we have one of these, and then we could have one or the other of these. Okay, so we're gonna build an atom here in a second. And that just shows you the nested nature of N. If N equals 1, then L can only be 0. That's it. All right, so zeros are S's. So 1S would be the sublevel designation. M sub L could only be 0. All right, if this is 0, you can only have 0 here. So the number of orbitals at N equals 1 is just 1. That's it. At 2, you could have 1 at, let me see, I need to do it over here so it shows up. There. So at 2, you could have L equals 0 or 1, which means for L equals 0, you still have only 1 orbital possible. But for 1 or P, you can have 3 because you get -1, 0, plus 1. So you can have 3 orbitals for that one. And then it balloons from there. So if you get down to N equals 3, you could have L equals 2, which is the D. Now you can have -2, -1, 0, 1, 2, and that means 5 orbitals, plus the 3 above it, plus 1. So you could have 9 possible orbitals there. Okay. So, principal quantum level N equals 3, determine the number of allowed subshells, different values of L. So how many different values of L can you have if N equals 3? Well, 3 means that you can have 0, 1, or 2. Right? Yeah, 3 levels, 0, 1, and 2. There you go. And we would designate them as 3, 3, 0. See, that's why we use letters. 3, 0 would be confusing. Is it 30 or is it 3 and is comma 0? So we use letters. So 0 is S, P is 1, D is 2. So we could have 3S, 3P, and 3D, those levels. Now, trust me, this is going to make sense because I'm going to translate this information over here. And then it'll make a whole lot more sense. What if L equals 2? Now, L could be 2 for, let's see, this one, or it could be 4, 5, 6. It could be 2 for any of those upper ones. But what are the magnetic quantum numbers, the M sub L's for 2? Well, it would be -2, -1, 0, +1, or +2. So you get 5 levels if L equals 2. So L equals 2 would be 0, 1, 2 would be D. D could have 5 sublevels. Here we go. All right. Now about the shapes, right? For the S, 0, the shape is spherical. Right? The orbital shape, probability shape is spherical. Only with n equals 1 for the 0, 1s is spherical with no gaps, right? We call those gaps nodes. Nodes are places where you expect the probability of finding an electron to be 0. So if we go up to 2s, right, the s orbital at the n equals 2, we get 1 node. So the shape is still spherical, but we represent it here. There's your node right there. And if we go to 3, you have 2 nodes right here and right here. If you go to p orbitals, the shape of the p orbital is kind of like a dumbbell. Right? I drew that earlier with a figure 8 shape. That's the p orbital, dumbbells. And notice that the p orbitals here, 1 here, could have a -1, 0, or +1 m sub l. So one of these would be considered -1, 0, +1. And their orientation is different in space. This is the easiest one for me to visualize because it points X, Y, or Z. Oops, wrong button. Okay, it went too far. Back up. There we go. So this is that was the P's. The D's have, remember, 5 possibilities, right? So their magnetic component, they're still kind of lobe shaped, except for this last one, right? You got these lobe shaped pointing in that direction. They're all pointing in different directions. And then this one has a donut in it. Now, these are artist's rendition of the solution to Schrodinger's equations. So when we put in these numbers into his equations, we get a plot that shows probabilities. Right? So this is not something that you would see with your naked eye, even if you could get small enough to see it. Right? This is a representation of maybe where you could find, it's most probable to find the electron in this orbital. And then F's are even wilder. You can have 7 F's, right? F equals, L equals 3, right? So that'd be -3, -2, -1, 0, +1, +1, +3. So you can have 7 orbitals, magnetic quantum numbers from L equals 3. All right. Now, as far as this last one goes, any one of these orbitals, once you get down to this level, that orbital can have 2 electrons with a maximum +1/2 spin or -1/2 spin. They have to be opposite spins in order to occupy that orbital. I mentioned Pauli earlier. Pauli's exclusion principle says in any given atom, no 2 electrons can have the same set of 4 quantum numbers. So this set of quantum numbers is unique for every electron. They can have the same this one, same that one, same that one, but once they get down here, they got to have different spins. But they can have any range as long as they're not the same set of quantum numbers. That's the Pauli exclusion principle. There's a problem that arises and has been tackled by numerous scientists over the years. Is that what do you do? What happens to these energy levels that you're specifying here in Schrodinger's equations when you get 2, 3, 4, 5, 6 electrons? You got those interactions, right? You got more protons pulling on them in the nucleus, plus you've got more repulsive effects of the electrons in your neighborhood. So that complicates the energy calculations even further. And my guess is that Schrodinger's equations were a starting point, and that fixes have been instituted over the years to compensate for different energy levels. And based upon chemical data. Okay. That's another reason for probabilities are the only way we can handle them, because we can't say exactly where the electron is and how it is affected by its neighbors. But we do know that as electrons enter the space around a nucleus, as we add proton, we add another electron for neutral atoms. Right? As we add more protons, add electrons, as we're building atoms, we do know that the electrons occupy the lowest possible energy state. Each time we add a new electron, it goes into the next available lowest electron energy state as we build them up. So the larger atoms are going to have electrons in these further orbitals out here when they're ground state, when they're neutral and not excited. What we do get, though, is as we add more protons and add more electrons, we get a shift in the energy levels that you would normally expect to see. Say, this is, generally speaking, the energy level is 1, 2, 3, 4, 5, 6. But notice, let's see, if we get this animation started off with the 2's being next to each other, 2s and 2p next to each other, 3s and 3p and 3b next to each other, 3d. But the animation showed us that if you add electrons to these, then what happens is you shift the energy level of the 2p above the 2s slightly, and the 2p above the 3s and the 3d above the 3p. So at some point, you could get an inversion where you could have 4s and then 3d would be a higher energy level than that. So that's one of the things that happens when we start adding more electrons as we're building atoms. And I'll show you where that occurs and how to tell the difference. And right, it's not as bad as it sounds. Not for us, it is. For the ones who created the system, yeah, it was probably a big headache. Okay, there's one other thing that we can discuss. It's called the penetration effect. So these electrons, as we add more electrons and we introduce higher energy levels using this quantum system, we calculate densities for electrons or probabilities of finding electrons in certain positions. And with those, introducing those nodes and the densities that occur between the nodes, we find that even though an energy level can have most of the probability of electrons out here, and then a higher energy level may be slid in underneath it, there's a portion of that energy level that has a probability closer to the nucleus. That penetration effect gives the overall energy for that, in this case, 2s, for instance. Let's see, that 2s would have a lower energy than the 2p based upon the penetration. I've got a diagram coming up here. I think it will help. Here we go. So our 2s looks like most of the electron probability is out here beyond the distance of the 2p. But remember, the 2s has a node in it right here. And inside that node is a significant portion of electron probability. So that penetrates toward the nucleus and overall gives the 2s a lower energy signature than the 2p. That's all we mean by the penetration effect. There's another possibility for the 3s orbital, has 2 nodes, but it does have some penetration toward the nucleus. And if you look at each one of the orbitals that are possible with the 3 SPD, we find that the S penetrates. Go. The S, okay. The S right here, the red one, penetrates deeper than the P, which penetrates deeper than the D. And that still gives us sufficient energy signature close to the nucleus that we count the S as a lower energy than the P or the D. And this is important when you start filling the orbitals, right? You need to fill the lowest energy first and work your way up. Okay. Let me check. I want to check myself and see how we doing on time. Okay. We're into lab now. Does anybody need a break? Everybody okay? It's kind of warm in here, isn't it? It is to me. Maybe not to you. I'm generating a lot of thermal photons here. Okay. So we're going to talk about the periodic table. In general, first we're going to talk about the periodic table in general, historically speaking, and then some of the major divisions of the periodic table. And then we're going to get into electron configuration for atoms and then correlate those to the periodic table. First, we want to introduce the periodic table. The first chemist that recognized groupings of elements that have similar properties was Johann Dobereiner. And he put elements together in triads, right? 3 elements together that had similar properties. Chlorine, bromine, iodine. Those are all halogens. They have similar properties. They behave similarly, not exactly the same, but they were similar. And say, if you reacted one of them with the same metal, say sodium, chlorine, bromine, or iodine would behave similarly with sodium. And there were other groups that he proposed. This was just one example. But that's as far as he went. He just put them together in those groups and let it go at that. Then along came Lothar Meyer. He was German. Let's see, where is it? There it is. Lothar Meyer. He arranged more of the elements. By this time, it was later than Dobereiner. He arranged the elements in groupings. And he was working almost simultaneously with Mendeleev, who was Russian. But the difference between the two is the way Mendeleev treated his information. He put them in periods, groups. In fact, his original table had the groups going from left to right. Right? These are similar elements going left to right. Now we have them vertically. And he said all these elements are similar, and he strung them together in such a way that their atomic weights, as they knew them in those days, they didn't know about atomic numbers yet. Atomic weights would increase this way, and then he'd get down here and say, wait a minute, that one has a similarity to this one. So he put it up here, and then he'd work his way down again. That's the period, right? Period. But I talked about that periodic motion. You know what periodic motion is? In physics, it's motion, but it goes through a cycle and comes back to where it was, kind of like a pendulum. So that's the concept we use for the periodic table. We go down as far as we can, and then the next one, the next highest one in atomic weight, actually has characteristics like this one. So we put it up here. We've gone through a period and worked our way back. So we go back back, 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 back. Now on this table, we go left to right. Okay, so Mendeleev put these together in groups and periods. And he noticed occasionally that there should be an element right here based on its weight. But the next one in order that we knew was more like this group down here. So he put it down here and left that empty spot. And not only that, he said, okay, one of these days, somebody's going to find an element and it's going to be like this group and it's going to have this weight and these characteristics. And he did that for several of them. And sure enough, they eventually found. So the fact that Mendeleev used his arrangement, his table, to predict the existence of yet undiscovered elements is why he gets most of the credit. Okay. So this is our modern table. In fact, the second, Mendeleev published a second periodic table a few years later, and he had, by that time, he had turned his groups vertical. So that's where they've been ever since. Similar characteristics are vertical. All right, so we can divide the table up into these groups. Have you done that? Did I have you do you've already done the special one, right? That special credit with the table.
Yeah.
Okay, so you know a lot of this stuff already. So we know that some groups have special names. Here we go. Alkaline metals, first group, alkaline earths, transition metals, halogens, noble gases, and the lanthanides here and the actinides. And then, of course, we had several in here. Oxygen group is the chalcogens, and the nitrogen group is the pnictogens. And then the rest of them just don't have names. So that's the way they're organized. And one that's missing here is these first two columns, and these last 6 columns are often grouped into what's called representative elements. Now, I'm not sure where they got that name, but I do know that when we talk about trends in the periodic table, and we'll talk about those also, the trends hold pretty well when you're talking about the representative elements only. When you get into the lanthanides, actinides, and transition metals, then the trends kind of get squirrely. Just a word of warning. Okay, we have the non-metals on the right, metals on the left, and most of the elements in the periodic table are metals. And then we have that group along the black squiggly line called metalloids. Depends on the reaction. Sometimes they act like metals and sometimes they act like non-metals. Okay. Another principle. We have the Pauli exclusion principle, like no two elements can have exactly the same. No two electrons can have the exact same set of quantum numbers. The Aufbau principle is a German word, and I don't know German. So near as I can tell, Aufbau just means this is how it's done. An Aufbau principle basically says what I said earlier. The electrons are added to orbitals lowest energy possible. As you add more electrons, you build them up from low energy to high energy. And when we write them in a shorthand linear fashion, where is it? Here we go. Linear fashion, we write them low energy to the left to higher energy on the right. And I'll show you how to do that in a minute. Hund's rule speaks to the pairing of electrons. Remember that very last m sub s number was plus half minus a half. When you have sublevels of the m sub l level, then you can go from, let's say n equals 3, and then L equals 2, right? 0, 1, and 2. So within this one, M sub L's, you can have -2, -1, 0, +1, and +2. And then inside these, you can have 2 electrons for each one. Okay? What Hun says is you can't start pairing up these electrons with plus and minus spins until you got at least one in each one of those sublevels. So you'd have to go, and I write the spins like that, up spin and down spin. So you got to have up, 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 up. Then if you have another one that needs to go in here, you can pair them up like that. But you have to have all up spins, so to speak, in these sublevels before you can go back and start pairing them. That decreases the amount of energy because once you pair them up, they're in the same region of space and they're going to be repelling one another. So this rule says you need to minimize the amount of energy repulsion that you have before you can start pairing. That's Hun's rule. And that's one way of looking at it. Your textbook, I think, uses boxes and double-headed arrows. That's too much trouble. I just use a line and a single barb, one way or the other. Okay. Valence electrons. Valence electrons are by definition the number of electrons with exactly the same principal quantum number. And they're the highest principal quantum number of the series in the atom. So in this case, you've got let's see. I'll lose there's my arrow. You got 2 electrons here, and you got 6 electrons there. So you have 8 valence electrons in that configuration. I mean, we need to learn how to do the configuration before I start talking about it too much. All right, here's what we're going to do. Let's take an example and write the electronic configuration for, say, oxygen. Okay, so neutral oxygen has 8 protons, which means it also has 8 electrons. So we have 8 electrons. So the lowest energy state is n equals 1, and it can only have S, right? One can only have a 0, which is S, right? So at that point, you can only have a +1 or a -1. Right? So we've got 8 electrons, we have to put 2 in there. Next level up is principal quantum number 2. Well, it can have a 0 or a 1 because that's 2, right? That's the 0 and that's the 1. Okay. So we've got 6 electrons left. We can put 2 of them here. So 2 from 6 is 4. That means we have 4 electrons left. They can go there. Now, how many can this one hold total? Well, this is L, so M sub L can be -1, 0, +1. Right? So it can have a total of 6 if we filled it up. But we only have 4, so it'd be 1, 2, 3, 4. Okay, that's what that means. And that is the electron configuration for neutral oxygen. 1s2, 2s2, 2p4. Okay, let's do another one. How about see, that was a non-metal. Let's do a metal. How about magnesium? Magnesium is 12. There we go. So we work our way up. 1s2, 2s2, 2p6. That's 6, 7, 8, 9, 10. We need 2 more. So what's next? We've used up all the 2s and s's and p's. We go to 3. 3s, 3s, 2. So that's 12 electrons. And notice, let's see, I think it's on the next slide. There we go. Notice that as you work your way up in the periodic table, you've got, here we go. Hydrogen is 1s1, helium is 1s2, then you go to the 2s, right? Lithium, beryllium, boron gets into the p's. And then we stay in the P's until we get all the way over to neon. And then we go into the 3s. And that's where we get to magnesium, is right here. Okay, so you can, if you know how the periodic table is structured, you don't have to remember that sequence. You just say, where is it in the table? And then I can work my way down to it. Notice though, you may have already noticed it. Here, once you get into the transition metals, you got 3s here and then 3p there. And then you go to 4s, right? That's logical. But then you go to 3ds because 3 can have 0, 1, 2. 2 is a D. But 4s is a lower energy than 3d because of that chart I showed you, which shifted the energy levels. So now 3d is a higher energy level than 4s. So we're going to put them into 3ds next after 4s until we get the D's filled, and then we can go back to 4p. Okay, all the transitions are like that. If you're in period 5, then the transitions are 4ds. If you're in 7s, the transitions are 6ds. If you're in 6 and you get to lanthanum, then after lanthanum, you go into Fs. It goes from 6 down to 5 down to 4F. Okay, we're not going to mess with those too much. Because even if you follow that pattern, there are some switcheroos in there, especially in the transitions. I'll have to, maybe I can show them to you later. But that's the format. Now, there's also a shorthand. Let me see if I'm stealing my thunder again. Okay. I think it's on the next slide. Yeah. This is if you don't have the periodic table available, this is the way you can tell what order the orbitals come in energy and filling them. So you draw out the possibilities, right? There's 1s, there's 2s, and you also have a 2p. And then at the 3 level, you have s, p's, and d's. And then at the 4 level, you have s, p's, d's, and f's. Right? And then at the 5 level, 5, 5, 5, P, D, F. We're not going to go to G's because while the G level does exist and higher, it's only useful for excited atoms, right? These are ground state. And then 6S, 6P, 6D, I think is all we need there. Then 7S and 7P. You can go on out, of course. But for our purposes, we're going to fill them in this order. Diagonal there, diagonal there, diagonal there. That's where we go from 3P to 4S and then back to 3D, 4P, 5S, and then back to 4D, 5P, 6S, and 4F, 5D, 7S. Okay, so that diagonal will give you the proper order of filling if you don't have the periodic table. If you got the periodic table and you know how it's structured, you don't need that, right? You can do it from the periodic table much quicker. Okay. Oh, here's some examples. Sulfur. Right. Look at sulfur. Okay, it's got 16 protons, 16 electrons. Okay. So we go 1s2, 2s2, 2p6, 3s2, 3p. How many? Well, let's see. Sulfur is in 1, 2, 3. Right. So 3p, 1, 2, 3, 4. 3p4. Now let's see if that adds up. 4 plus 6 is 10 plus 6, 16. So we're good. Now, an abbreviated way of doing this is to look at what would be 1s2, 2s2, 2p6. 2p6 would be neon. So neon 10 We have the same structure here. And then beyond that, we have 3s2 and 3p4. That's a super shorthand. And it's very useful when you start to get to really, really big atoms like barium. Let's do barium. Let's see. Sulfur, there's sulfur, okay. And there's your shorthand. And barium has what? Barium's way, way down here. 56 electrons, okay? 56 electrons. Okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. How many? How many levels of D under D? 5, right? 5 levels with 2 electrons each would be 10. And if you count, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 electron each incremented. And then we get 4p, 6. And where are we at now? 4. 1, 2, 3, 4p6 is that krypton. Now we got to go through 5s, 5s2, and 4d10, and then 5p6. And 5p6 gets us to here, right? 1, 2, 3, 4, 5, 5p6. Now we have 6s. I got to swing around. 6s2 gets us the barium. Right? If we count them up, let's see, that's 10. And that's 10. That's 20, 30, 40, 52, 54, 56. Okay. Shorthand. Work your way back until you find a noble gas. Right? So 6s2, work our way back, xenon 54. So xenon 54 is the core. And that covers everything from here over. And all we have left is 6s2. So that's the shorthand. Okay, let's see. Oh, it just gave us the shorthand. Europium is, well, that's good shorthand. Notice that we've gotten down to 6s here. And then when we get to lanthanum, let's see, lanthanum here, then we shift down because there's a break here. We go down here to europium. And it's 1, 2, 3, 4, 5, 6, 7. Yeah, 4f7 is europium. But I'm not going to hold you to those guys because they really get messed up. We will talk about some of the other discontinuities that occur, say, in here and along in here. I'll mention those. Now we're going to talk about trends in the periodic table. Yeah, okay. Well, I guess is that in the next chapter we talk about those discontinuities? Maybe it is. So I'm going to let that rest for now, and we'll cover that later if it crops up. Okay, these are the 3 major trends that we're going to talk about in the periodic table. So what do we mean by that? Well, if you go from left to right, top to bottom, you see certain changes in these physical properties: ionization energy, electron affinity, atomic radius. We have to define our terms, of course. So we'll start with the ionization energy. What does that mean? Ionization energy is defined by that equation right there. So if you have one atom or one mole of atoms, they need to be in the gaseous state. Then when you add energy to them, you will get a singly charged gaseous atom plus an electron. What that means is, how much energy does it take to eject one electron from that atom? That's ionization energy. It's usually a number of joules per mole, right? So 6.022 times 10 to the 23rd atoms. But this would be the equation. Notice that this atom must be in the gaseous state before you measure the energy required to eject the electron. And that's practical reasons, right? What if it started off in the solid state? You'd have to add energy to make it liquid, and then add energy to make it gas. And then you got enough energy added to make an electron eject. Well, how much of that actually went into ejecting the electron, right? You don't know unless it's a gas first. So it has to be a gas, neutral. Then add energy, and that's the ionization energy. Ionization energy can also be multiple. So if you have, our example is magnesium. So if we add enough energy to eject one electron from magnesium, it's 735 kilojoules per mole. That's the first ionization energy. The second, we take that ion in the gaseous state and eject the second electron. Takes more energy, right? That's purely electrostatic. Well, not purely, but largely electrostatic, because you're trying to move and remove another negative from an already positive, right? There's an attractive force there that you have to overcome, right? So it takes more energy. And then the third ionization energy, you have to add even more energy. Now notice that this one is about double the first one, but this one is like 7 times as much or 6 times as much, right? The reason for that is best explained if we know the, well, we already did this one, didn't we? If we know the electronic structure of magnesium, 2s2, 2p6, that's 10, 12. And wait a minute. 1 is 2, 6. That's 10. And then 2, 3s2. There we go. Okay, the first 2 ionization energies remove an electron from this high energy level, 3. Right. So it takes a certain amount of energy and then about twice that to make the second one. Once you get past this one, those are valence electrons. They're the ones that are out there that do the chemical reactions. Once you get below these, you're into the core. And it's typical. When you get into the core to remove electrons, the energy required goes way up in a hurry. Why? Well, because this is a very stable configuration. Right? 2p6 would be like neon. Right? Noble gases are not noble for no reason. Right? They're not inert for no reason. Their electron configuration is complete. Right? They don't need any more, and they don't want to give any up either. So once you get down into the core, you're talking about noble gas configuration. And when you try to remove electrons, if you try to move an electron from first ionization energy from neon, it would not be much less than magnesium at that level. Okay. All right. So that's the first thing. Once you get down into the core, the energy required goes way up. We haven't said anything about trends yet, have we? Okay, here are the trends. In general, as you go from left to right across a period, the first ionization energy increases. Okay? Why is that? It's largely due to the fact that you're adding more protons. You are adding more electrons, yes, but you're adding more protons, and the electrons are sitting there at roughly the same energy level, right? whereas you're adding more protons and they're drawing on those electrons much stronger. So the first ionization energy is going to go up as you move from left to right. Okay. And that's described as increasing nuclear charge, just adding more protons. Nuclear charge, it's not strictly speaking just the number of protons. The increasing nuclear charge can be modified as the atom gets bigger. So as the atom gets bigger, you get more electrons in the core down below, and they have a shielding effect on those positive charges. So, let's see. Yes. As you go, was it on the next slide? As you go down in a group from top to bottom, the ionization energy decreases because the outermost electrons are far away from the nuclear charge, and the inner core electrons are shielding that, partially shielding that positive charge. So as you get bigger and you're adding electrons to higher energy levels, it takes less energy to go from that to infinity, which is what you're doing here. So as you go down, the ionization energy decreases, or as you go up, it increases. So overall, the trend of ionization energy increasing is from lower left to upper right. Okay. All right. Let's see. We want to spend time on this one. First ionization energies in the first 6 periods. What we'll notice is, look at these noble gases. First ionization energy for helium is way up here because the electrons are very close to the positive nucleus. Then you start getting some shielding in the neon, and the argon even more shielding. Krypton, so we're moving down in a group, and we're seeing a decrease in the first ionization energy. That makes sense. And you can do that with any of these. But if you stay in the period, you notice from left to right, hydrogen to helium, you increase. From lithium to beryllium to boron to nitrogen, oxygen, general trend is increasing from left to right on each one of these. These little dots right in here, those are transition metals. So they're kind of squirrely, right? They jump up and down. What you'll also notice is, notice here, nitrogen is a higher first ionization energy than oxygen is. Right? If the trend were absolute, then oxygen would be a higher first ionization energy than nitrogen, because oxygen is to the right of nitrogen. Right? So it should be a higher energy here, but it's actually lower than nitrogen. So here's the explanation for that one. The configuration of nitrogen, 7 here, oxygen is 8, right? We did oxygen earlier, 1s2, 2s2, 2p, 4, 4, 4. And this one is 7, so it's 1s2, 2s2, 2p3. Okay? So what's the structure here? Well, this one's got 2 electrons there, this one's got 2 electrons there. That's no big deal. But this one has 3 sublevels, -1, 0, +1, and it's got 3 spin-up electrons in it, right? Because of Hund's rule. But on the side of oxygen over here, we got 1, 2, 3, 4. So what's the first electron that's going to be ionized? Well, in this one, it's one of these, right? All by itself. This one, that one is at the highest energy because it's paired with another electron with that repulsive force. So it's going to take less energy to get rid of that one than it is to get rid of this one. That's why the reversal from nitrogen to oxygen. Oxygen takes less energy to eject that one than nitrogen would take to eject that one. And that trend, you can see it in several places in the periodic table. The general trend, though, is from lower left to upper right. It's increasing with these anomalies. All right. Let me see how close are we getting. Not too far. Okay. All right, I did steal my thunder. The ionization energy discrepancies are largely due to electron repulsions. And oxygen is a perfect example. When you get those two electrons paired, they're more repulsive toward each other, which makes less energy required. So you have beryllium to boron, nitrogen to oxygen. Those are two examples for the second period, right? But you can see those trends also in the third period without too much difficulty. So, generally speaking, which one requires more energy to eject an electron, sodium or chlorine? Let's see where they are. Sodium, we're in the third period, sodium on the left-hand side, chlorine on the far right-hand side. So ionization energy increases to lower left, upper right, or from left to right in a period.
And then it would be more. Sodium on the far one.
Chlorine,
Backwards.
yeah, backwards. Ionization energy increases left to right. There you go. How about lithium and cesium? Now we're in the same group. Lithium's here, cesium's down there. So cesium should take less energy.
The decrease is going down.
Yeah.
Lithium will take more.
Lithium will take more, yes. Okay. Which has the larger second ionization energy? All right, so now we have lithium versus beryllium. Lithium and beryllium. So lithium is only 3, beryllium is 4. So lithium is 1s2, 2s1, and beryllium is 1s2, 2s2. So the first ionization energy would give us what? We have 1s2, 2, that'd be it. Right, just 1s2 would be left, and that one's gone.
Yeah.
Beryllium would be 1s2, 2s1. Okay. So how about the second ionization energy? For lithium, the second ionization energy is pulling from the core. It's going to be much, much higher than this one, coming from another valence electron. So lithium should have the highest second ionization energy, simply because it's coming from the core. And this chart comes out of your book, and it just illustrates this jagged line, shows you where the core is for each one of these atoms, right? So for phosphorus, you've got to get to the 6th ionization energy before you get into the core. Whereas magnesium, we showed that one earlier, the 3rd ionization energy will get into the core. Aluminum will take the 4th ionization energy. We spend a lot of time on ionization energy because it's the easiest to understand, I think. Now we're going to talk about electron affinity. And the common misunderstanding is that the electron affinity is just the opposite of ionization energy, but it's not. We base it upon this formula. Gas again. Now we're adding an electron to a neutral atom. Right. So, should this be endothermic or exothermic? It should be exothermic. As an electron drops down from infinity and captured by the atom, it gives off energy. So we should get energy from. In other words, the value of the energy should be negative about system versus surroundings. right? Think of the atom as the system. It has to give up energy to get that electron. So it's the value for the energy will be negative. And the larger the negative value, the more negative it is, the more energy you get from that addition. Okay. All right. So it needs to be gas, electron, gas in order to be considered electron affinity. How strongly does this neutral atom want an electron? Okay. In general, as we go across a period from left to right, the electron affinities become more negative, which means the pull is stronger because it's exothermic. Okay. And as we go down in a group, the electron affinities become more positive. In other words, the atoms don't want the electrons as much as you go down in a group. Okay. And we don't give an explanation. The explanation, I think, is similar to ionization energies. In fact, that as we go from left to right, you have more nuclear charge. And the higher nuclear charge is more attractive to the electrons. But even then, as the electron approaches, it has to give up more energy. All right, atomic radius. That was electron affinity. Atomic radius. Atomic radius is kind of, it's like watching a tennis match. Right? Going back and forth like that. But atomic radius depends on who's defining it. Like, what is the radius? And it depends on whether it's a metal or a non-metal, or whether it's high in the periodic table or low in the periodic table, as to which method gives you the best estimate for atomic radius. Right, atomic radius considers not just the nucleus, but the electron cloud that surrounds it. Right, so how do you know where that is? Because it's kind of nebulous, and we've already learned that it's not fixed. Right, there is uncertainty there. So we have to take every estimate with a grain of salt. If you are able somehow to determine the distance between the nuclei of the two atoms, then you take that distance and divide by 2, and that's your radius. That's one way. You got it, but the question is, where is the outer limit? Where are they actually touching? Right? How do you determine that? Major two types of determining the radius are for metals, right? Where metals can be packed in close together, and we can determine experimentally like how many atoms are in a row, and then we can work our way down to individual 2 atoms. This is often measured by X-ray diffraction, and we get into that in the second semester. But basically what it says is you've got a row of atoms here, and you got a row of atoms here, and you fire X-rays at it. And the X-rays bounce off here, and they bounce off here, and they bounce off multiple layers, right? And when they do that, you set up a pattern of interference, constructive interference and destructive interference. And you can angle your detector so that you find out where those peaks of constructive interference are, and then use a formula called Bragg's formula, which you won't get until next semester. And you can determine the distance between those atoms. And that's what we use for metallic radius to determine that. I used to use that on, not regularly, but I did for my PhD work on clay particles. soils are made up of, well, some around here, they're made up of a lot of rocks, big rocks. And then you get down to the level of sand and then silt and then clay. And really the interesting reactions that go on in soils happen at the clay level because there's lots of surface area. So we want to know what kind of clay is it that's in that soil. So I went to a lot of trouble to physically sift through the soil and then isolate a small section, and then I put it in a graduated cylinder with a special solution that would keep the clay particles from sticking together. And we would use another principle, Stokes' law, to determine how fast those particles settle based on their size. And then after they get down to a certain level, I'd lower my extractor and suck up some of the fluid. And I knew that at that level, there was nothing but clay particles. So then I'd take a drop or two of those and put them on a glass slide and let them dry. And as they dried, the clay particles like little plates. So as they dry, they sort of settle down into a single layer, stacked layer. Then I can put that into my X-ray diffraction and fire X-rays at it and measure the distance between the layers in my clay particles. And that would tell me what type of clay it was. All right, so there are practical applications for this methodology. For non-metallics, where you have covalent compounds together, what you have to do, in large part, we're looking at the diatomic molecules. If you can create homonuclear diatomic molecules, then you can use other forms to investigate what's the distance between them. Sometimes X-rays, sometimes firing electrons at them, sometimes neutrons, microwaves. There are various types, but those are the two major divisions: metallic radius versus covalent radius. Covalent radius is probably underestimating the distance or the size of the atom, because when you form a covalent bond, it draws those nuclei closer together and there's a lot of overlap. Right? So the metallic radius is probably closer to the actual atomic radius than the covalent is. Okay. So in general, as we go across a period from left to right, the atomic radius decreases. And that's largely due to the increase in nuclear charge. The electrons are being added to the same principal quantum level, right? It's either 1, 2, 3, or 4 at that level. But the nucleus is increasing in charge. And what that does is it draws the electrons closer. So the radius is going to decrease from left to right. If you go down in a group, you're adding electrons to higher quantum levels. So they're sticking out here like this. Plus you've got the shielding effect of the core electrons. So as you go down in a group, they get bigger. And here's a chart of the various atomic radii that have been determined. And you'll notice that we skipped over the transition metals, right? These only show the representative elements because they're more well-behaved. Okay, which should be a larger atom, sodium or chlorine? Now your answer's right. Sodium, right. There we go. Sodium is a bigger atom. How about lithium and cesium? Yeah, cesium is going to be bigger because we're adding electrons to higher quantum levels. Okay, now let's see. Talking about orbitals, which is larger? The hydrogen 1s orbital, 1s from hydrogen, or the 1s from lithium? Well, hydrogen only has one proton. Lithium has what, 3? Yeah, lithium has 3 protons. So what we're getting here is lithium is oh, excuse me. 2s. Actually, it's 1s with 2 electrons in there, like that. Okay. So, which is larger, the hydrogen 1s orbital or the lithium 1s orbital? Well, the lithium 1s orbital is feeling the pull of 3 protons, but the hydrogen is only feeling the pull of 1 proton. So this 1s orbital should be bigger than that one. Did I say that right? This one's bigger than that one, yeah. Which is lower energy. Lower energy is based upon distance from the nucleus. So if this one is closer to the nucleus, it's smaller than this one, then this one should be lower energy. Okay. All right. Let's see, how are we doing on? Ooh, am I getting close? I'm getting warm. Got 2 more slides on my set. If my hard copy is consistent with this recent edit, arrange the elements oxygen, fluorine, and sulfur according to increasing ionization energy. So I assume that's the first ionization energy. Okay. Oxygen, fluorine, sulfur. Increasing ionization energy, lower left to upper right. So there's oxygen. So we know fluorine should have a higher ionization energy than oxygen. How about sulfur? Sulfur is below oxygen, so it should be down here. So sulfur, oxygen, fluorine should be the order. Okay. How about atomic size? Let's see. All right. Sulfur should be the biggest of all of them, I think. So sulfur should be bigger than oxygen. And oxygen should be bigger than fluorine, I think, based upon where they're located in the periodic table. Okay. Okay. Oh, final thoughts. An atom's chemistry is based upon the number and type of valence electrons. So those outermost electrons that we identified as valence are the ones that are responsible for chemical reactions. The core electrons, I don't know of a single chemical reaction where core electrons are involved. It's always the valence electrons. Electron configurations can be determined from the organization of the periodic table. Yes, indeed, they can. You can make it, you can draw the configuration a lot quicker if you know how the periodic table is structured. And we got lots of practice there for you. As usual, certain groups in the periodic table have special names. Yeah, we went around those. Basic division of the elements in the periodic table is into metals and nonmetals. Yes, that's true. And that's the end. Okay. Let's see. I only had, as far as I know, I only had 1 Zoomer today. Yeah, Bryn's still there. Okay, that's it. What we're going to do next. On your schedule, next Thursday is a buffer day. So we can use that to go over the lab. And then the following Tuesday will be a review day, followed by, I assume, an exam on Thursday. Yeah.